Now we'll start our first session with the topic Overview of Learning Methods and Systems. For this talk, we are pleased to welcome Dr. Ramakrishna Grothi. Dr. Grothi is an associate professor at IIT Tirupati, Department of Electrical Engineering since 2017. Prior to this, he was an associate professor at Indian Institute of Space Science and Technology, Trivandrum, since 2011. He was also a postdoctoral fellow at India, France. He pursued his master's in ISC Bangalore and PhD in IIT Madras, both in the field of computer vision. His teaching experience spans signal processing, computer vision, image processing, machine learning for image processing, and deep learning for computer vision. He has around 18 years of experience and expertise in the development of various image processing and computer vision applications like image restoration, in-painting, visual tracking, 3D reconstruction from active and passive stereo. Sir, please continue with the first talk.
Okay, good morning to you all. I would like to make this session interactive. So whenever you have any doubt or question, feel free to interrupt me or stop me and ask. This talk is a generic talk just to give you an overview of the area of learning methods and systems. So it's not in particular to a specific specific details of a particular learning method. So I will try to I will try to give a basic brief of or introducing the learning methods itself at the beginning. So probably you may be, many of you may be from different backgrounds. I see that the students are the participants ranging from first year of BTech computer science, and then some in ECE, and then just finished their BTech in ECE, and some have completed their probably masters and even PhD, and then working as faculty and so on. So the broad spectrum of participants is good in some sense, and I would like to take you all to the basic requirements or the basic skills that are required to work in this domain. So I will probably first introduce from the very elementary aspects that we usually sense and see are the kind of subjects that you study, like signal processing kind of subjects, to the need of learning. And then we will see a broad spectrum of learning, and we also see the current methods of different learning methods and systems. Finally end up the discussion with the emerging or breakthroughs in this learning methods and systems. The overview of the whole workshop is already discussed. So the workshop is also is aimed to give you a exposure and the basic foundation in learning methods. Basic foundation in learning methods are the basic skills required for understanding the learning methods, and subsequently an exposure on the current state of the art in the learning method. So where to look for and what to look for, some such details you will be essentially understanding or maybe getting from this workshop. And you also be aware, if you would like to work in this area, or if you want to if you want to pursue your higher studies or research or any further in this area, what are all the basic methods you should understand, the references for them and so on. The objective is to make you be aware of all these things, and then the workshop gives an overview of this. So as I mentioned, the my talk starts with the usual perception that humans have, and then the little bit of understanding of what essentially the computers or the machines perceive, and subsequently what is the difference between them, and how do we move towards the ability that human have in terms of learning from the perception. What's the gap, and how do we, if you want to learn that, what are all the basic elements that are required. Let me start with a couple of questions and then we will move on to the some discussion on what is needed in this domain. So, what do you think is a major difference between, say for example, the talk, the title of the workshop indicates learning methods and systems. So, what do you think is that we will be discussing? Probably you might have seen brochure also, and you may have seen the whole talks, details of the title of the talks. So, I would like to know from you, what do you think we will discuss in this workshop? And also I would like to know what is the difference between the human perception and the machine perception. So, these are the two questions. Any of the participants are welcome to answer. So, let us start from the difference between the human perception and the machine perception. So, what do you think is the difference? When we perceive a sound, for example audio, or when we see an image, or when we want to learn something, okay, versus a machine want to learn, what do you think is the difference? Any answers are fine, there is no particular answer that even I know. Okay, okay, fine. What else? The methodology is what we are more interested in. Of course, speed is one aspect. Any other things? What are the differences in terms of the learning by the, if you would like to make a machine learn versus make a person learn? Yeah, feel free. Yeah. Training. Okay. Okay. So, we will see some of those, and say if we ask you, leave the machine learning, okay, or learning methods in general, come to the human learning. So, how do we learn, or say what all we can do by learning? Okay, remembering. Okay, what else? What all, say we seamlessly do many things, and those we might have already learnt. What are those seamlessly doing things that we have already learnt? Some examples you can give, not even on the methodology. We are interested in some examples of using learning in humans.
Whenever we are speaking, so we will take the feedback of whatever we are speaking.
Yeah, so we can we can also see the feedback of the speaking, okay, and we can understand this. If somebody says something, we are able to make meaning out of it from the speech or from the discussion. Okay, what else? What else do we usually do that we already learnt? Of course, all of us learn it by default. So, and we use them. What all the other things that we usually learn and use them? Okay. So, when we see, for example, this class, okay, you may see that there is a talk going on. That's already is it's understood, or it is by default we have learned to know it. If we see any scene, okay, we can interpret it. So, that learning of who are persons, or what all the objects in it, we are able to see and then interpret it. Okay, and by touch we can say what it is. By smell we can say what fruit it is, or what it is to some extent. So, these are all the things that through the senses we already have learnt, and we use them almost by default, unintentionally or even. But when it comes to learning of the machine, or when it comes to exploring any methods of learning in the computer, what are all the challenges that we face? Let us try to understand. So, before we move on to that, I just want to listen and tell what these sounds are. What is the difference between the first signal, okay, second signal? What do you think is the difference between these two signals?
Noise.
There is some noise, very good. So there is some noise in these two signals. So now the question is, we want to remove this noise. This is the one operation we would like to do with the computer. What do you think we can do? Any idea on say how does a computer deal with this kind of scenario? Say for example, any sound signal that we have just played is for us it looks like a like we know that it is a speech or it is a dialing or whatever. So we recognize in that way. But how does a sound signal is being recognized by a computer? Okay, this is one question. If we know that, then we will see actually what is the difference between these two sound signals that are being recognized by a computer, and see the difference, and then we would like to say based on the difference that it sees, we would like to do some undo some operation, okay, for removing the noise. Fine? Okay, that particular such things are called processing. So this is actually the signal 3, is it close to signal 2 or signal 1? It is close to signal 1. So it is the denoised signal. Okay, so it's processed. We will see in the next slide what processing is being done. So what's that? Enter. So both appear same. Any difference you see? Yeah, you see slight difference, but more or less they are same. But I say that actually in computer, if I want to store the first signal, okay, I need some memory, right? So to store the second signal, I need 1/6 of the memory. So that means I have compressed the signal and stored, but still it roughly looks like the same signal. Yeah, so essentially if we would like to do say our requirement in terms of handling these signals or images or any different data or the problems is not necessarily putting at one place. We would like to say communicate and transmit them also. So we would like to see that how effectively they can be stored with lesser number of memory and so on. So there is some processing again has gone there. So let us see now some of the aspects of what processing has been gone there. See, you can see that the first signal is what you have seen as the signal 1, first original signal. Okay, and then the second one is what? Second one is noisy signal. So what kind of noise do you think it's added here? So this is the first signal and this is the second signal. What do you think is the kind of noise that is added here? Any guess? Any guess? Wild guess is fine. Okay, so it is some guess. With guess I would expect some answer. White noise. Okay, very good. What else? What guess? Why do you say it is white noise? Constant noise, is it? All frequencies, but this is not in frequency domain. Okay, please note that the signal is plotted in time domain here. So there are 16,000 samples. So if I sample, for example, 4,000 samples per second. Okay, so I might have taken 4 seconds of the audio, and that is this here. Okay, just 4 seconds of the audio. Okay, and dialing, and this is another 4 seconds. It's in time domain. This is in frequency domain. Okay, so in frequency, by looking at the frequency domain, you can tell probably what kind of noise is that. This is the frequency domain. Tell some quick answers. Sinusoidal noise, very good. It's because sinusoidal noise is added, you are able to tell because there are 2 peaks in the frequency domain here. Okay, so if you take any sinusoid and take Fourier transform, okay, most of you might have seen or known Fourier transform, right? So if you take any signal into the frequency domain, if it is a sinusoidal signal, it gives 2 peaks. Okay, so now if I want to remove this noise, okay, what should I do? Any guess on that? This is these 2 frequencies are because of the noise. Okay, and this is the frequency spectrum. Okay, 0 to 3000 Hz. Okay, is here, and there are 2 frequencies because of the noise or corresponding to the noise. Now if I want to make this noise free, what should I do? We will apply some kind of filter, and then filter these two we will not pass these frequencies and pass the rest of the frequencies. Okay, so that is referred to as filtering. So we have applied here, it's because some kind of filter. Okay, so they have applied low pass filter, sorry, low pass filter, and then knocked off all frequencies including that peak frequencies. Okay, so and then this is the filtered signal, and filtered signal, when we played, third signal is the filtered signal, that is looking almost like the first signal, right? So here, is there any learning happening? Is there any learning happening in this? This is also a kind of processing that we would like to say when we listen, for example, a noisy speech or noisy dialing even. We know that there is noise, we also know that there is dial. Okay, so we already are aware that there is a noise free signal, and we can also make out of the noise free signal in most of the times. Okay, if the noise is not too much, we will be comfortably able to make, and there is some learning that we think that goes on within us, and we are able to make it out. But here there is no learning as such. What is happening here? This is called processing. Okay, this is a part of kind of signal processing we can consider. Okay, so there is a signal that is seen as one-dimensional signal or one-dimensional sequence of numbers. Okay, sequence of magnitudes of pressure variations. Okay, for the sound signal, and that one-dimensional signal, okay, we process in some sense. We may do either in time domain directly or in other domain. Okay, or we directly do or transform and do some processing. After that, we are able to see that, okay, whatever the operation we would like to perform is done, and we are able to see noise free signal. Okay, so here so far is only processing that has gone. So now this is the second example. What do you think is in this example happening? Can some of you guess what may be happening here? This is the original signal. Okay, and then I said there is compression, right? 6 times we have actually compressed the signal. That means the memory occupied by the first signal is 6 times more than the memory occupied by the second signal. Okay, here in this example. Then what is that happening? This is in the frequency domain. Okay, these two are in time domain. Okay, and the original signal and the reconstructed signal, they look alike, almost alike in time domain, right? But in frequency domain also they look alike, but there is some difference you can see. Those who can identify can tell. What is the difference that is happening in the frequency domain here? This is the original signal and this is the compressed signal. What do you think is the difference here? What is the difference we are able to make out? Look exactly alike? Huh? Okay, tell, fine, you are correct, but any reason for not being dense? See what has happened, we are making some of the very low frequencies which we consider as noise to be 0. Okay, so sorry, low magnitude frequencies we are making to be 0. Okay, so any frequency having the magnitude lesser than some threshold, we are just putting a 0. That means you need not represent that when we send them, okay, when we transmit that signal in frequency domain, for example, then we only transmit the non-zero frequencies. Okay, we location of the non-zero frequency and then the magnitude of the non-zero frequency. Where all it is 0, no need to transmit anything. So by that we can arrive at the compression. So this is also, is there any learning happening here? Yes or no? No learning happening. Okay, this is also a processing. I am just thresholding in the frequency domain, nothing else. Okay, so I take, say for example, if I have a vector x, okay, I apply y equal to a into x. Okay, just a matrix transformation. Okay, after getting this matrix transformation y, I just threshold. This matrix transformation can also be Fourier, okay, Fourier representation can also be put into the matrix and then transform, that's all. Okay, so I just applied a transformation to the signal and then made some small operation and then are able to compress. So either denoising, compression or many other applications, okay, can be done effectively through processing. Fine. So this is an example of an image. how does an image, see when we see an image, we know that it's, we only make out the persons or the objects and so on. Okay, you don't make out any pixels out of it. But when computer sees, it doesn't see it as a person or a object or anything. It doesn't see it as the scene or inference and so on, okay, from the picture. What it sees is a two-dimensional array of numbers, nothing else. So if we have a camera here, what does camera do? Each of the sensor element in the camera looks at a small region in space, okay, it averages the reflectance in that area and puts it as a value here. If that is bright, then the value is close to 255. If that is dark, it will put a value close to 0. Okay? So if it is in between, it 120 or whatever. So based on the intensities, okay, we have the corresponding the region the sensor element looks at. If we say 1 megapixel camera, for example, what do we mean by 1 megapixel camera? We have 10 power 6 pixels in it. Okay, 1000 cross 1000 pixels in it. So each of these 1000 cross 1000 sensor elements, okay, will look at small regions in space and average the intensities and puts a value there. Okay, like that it will see the whole sample, the whole space. Okay, and then you have the intensities in that region in which the sensor element looks as a value. So essentially the image captured, grayscale image that is captured, is a two-dimensional array. If it is color image, RGB channels, each channel will be R intensities, G intensities and B intensities. Okay, so that's what essentially a computer looks at. Now, if I want to make anything happen like humans want to do in computer, okay, I cannot do in the same way that humans does. So we need to understand its language, okay, and then we need to play with these matrices or matrix elements to make whatever we want to do. Okay, so now let us assume that our objective is to find out what are all the objects in a image. So assume that we have taken one image of a class or whatever, okay, and then we want to find out which objects are there in that image. What do you think? How do we think we should approach now? We have seen an image how computer looks now. So if I want to identify different objects in that, what do you think is the first step, or what do you think that we should do? Any guesses? What do we want to see? Like say, what does computer want to see to identify? Say assume that there is a small image with 5 different objects, okay, placed at different locations. Now I want to know that there are 5 objects by the computer program, okay, or computer processing. What should we do? What do you think we should do? What is the first thing that we should do? Any guesses on that? Very good. So we want to identify the boundaries. So I assume that that is what is one of the operation, okay, of image processing. So we can identify the boundaries by some operations, or say this is referred to as edge kernel. Okay, so essentially what we are doing is, say if I want to find out any horizontal edge is there or not, what we want to do is we want to see the pixel difference between the elements of the row 1 row above and 1 row below. Okay, if I do that 1 row above minus 1 row below, what I will get? Essentially if I consider this as horizontal edge, I will get a horizontal edge. Okay, so this is used not only at one location but used at all locations. At each location what I am doing, the difference of these pixels minus these pixels, these pixels minus these pixels. Okay, and then I get the gradient information. Wherever the gradient or change of intensities are high, okay, I say that if their gradients or the change of intensity is higher than a threshold, I say it is edge. If it is lesser than a threshold, it is not an edge. That's all. Okay, so similarly I do in x direction and I also do in y direction. Okay, so I also get some horizontal edges and then vertical edges, and then probably I will take, if I want to only all together, root of gx square plus gy square kind of thing. Okay, put together horizontal and vertical to get the overall edges. Okay, so this is also a processing we do for getting the edges in an image. Okay, so the image processing essentially deals with, signal processing deals with understanding what different kind of processes we can do on these signals, okay, to perform different operations that we have discussed so far. So, and many more such operations. And image processing does how to perform such operations with images, two-dimensional signals. Okay. So, a typical operation that we would like to do, we have done just now, is called convolution. Okay, those who know from EC background knows convolution very well. You might have studied it in some context. Where do you study convolution? Okay, where we first study convolution, where is it introduced? LTI systems. So, when you want to see the response of any system, you give an input, arbitrary input, okay, and want to see what is its output. Okay, first you should know the characterization of an LTI system by an impulse response. That means give an impulse input, see the output, impulse response, and from that, given that impulse response, give any arbitrary input. Now, convolution of this arbitrary input and impulse response will give you the output for any arbitrary input that you have. Okay, so this is exactly same thing we are doing here. What are we doing here? Essentially, we are doing the convolution of this kernel. Okay, this input we are giving and seeing the response for this, say this is impulse response, sorry, this we consider as the impulse response of the system, okay, and this is the input image, and input image is passed to this system and you get the output as this. Okay, so essentially we are doing convolution of this. Convolution means what? Okay, put at every location of the signal, and then of course you flip and put the signal, small impulse response signal, and then add all the elements after element wise multiplication with h of n and x of n at that location. Okay, that's what is essentially done. You are also putting this, okay, element wise multiplication sum, and you are giving the output as this. Okay, so essentially this is what the convolution operation that we are doing in processing. See, one thing that to notice, if I want to find out edges, I will find out an impulse response or a system, okay, that also is characterized by an edge. See, if I see only this, if I plot this, how does it look like? This is a step edge, okay, 1 1 1 like this, and then 0 here, and then minus 1 1 1 like this. Okay, so the filter itself looks like an edge, and hence if I do with that filter a convolution with an image, I am able to get an edge. Okay, highlight the edges. So this is roughly the kind of processing we do. If you want to highlight some regions in an image, we convolve with that kind of filter. See, if I want to find corners in an image, what do you think I will do? I want to find, rather than edges, we want to find corners. Okay, where are the sharp corner points? Okay, are the points where there are corners in an image. What do you think we will do? We will take a filter of corner. Okay, that means a middle value should be high and all other values can be small, and then such a filter we will convolve with the image, I will get the corners. Okay, so essentially if I want to identify different shapes in an image, say if I want to find face in an image, what do you think I will do? Just as an example, I have a big image, okay, in that I want to find out where the faces are. Okay, what do you think I can do? Any guess given this discussion? I somehow find the a filter looks like a face, okay, wherein say for example, usually eyes are dark and then middle nose is white. So I will take, so two black and middle white, okay, that is one filter, okay, and then this forehead is white and then this is black. So one filter white and black. Such filters I take and then do convolution, I get highlighted those regions and then I say that here is face. Okay, there hit happens for those filters. Okay, essentially if I want to identify any object, I need to design a filter that looks like that object somehow, that class of object. Okay, so and then I perform convolution and get. So this is also a processing, but still so far what we have done is the understanding what usual operations that happens in signals. Say if you want to perform any operation, usually that is required like denoising or any the way that we perceive. If you would like to see free from noise, free from here blur. Blur means what? If there is a car moving and if you take an image of the car, what will happen? The car image gets smeared. Okay, it doesn't look like a nice car. Okay, and but we would like to have the car back. What do? We need to do again a processing there. Okay, the processing there is, it is already smeared, that is averaged version is what you are seeing. So undo the averaging. Okay, that is called deconvolution. You already, there is convolution. The convolution means there is a averaging that has happened. We want to do something of inverse of operation, averaging. Okay, some kind of differentiation is to happen. Okay, so such processings can give us effectively the way that we would like to see the signals, perceive the signals. But what is the limitation of it? Why do we need to go for learning at all? Okay, that is what we discuss now. So before we go to that, see, assume that are we just interested in processing? If there is an image, okay, yes, I would like to know what is there in that image. See, if after processing we have seen the edges, but edges is not the end. Say for example, here the problem is how many razors are there in this? I would like to know, count. What should I do? I have found somehow edges. What do you think next I should do? Any guess on this? So we have a razor image and we have found the edges of that image. Okay, got the boundaries. Now the next step is we would like to know how many razors here. So this is called inference. Okay, processing is to the input is also a kind of signal, image or audio. Output is also a signal. That is essentially any processing, either signal processing or image processing does. But we will not be able to, or we cannot stop there. Like the humans perceive and infer, we also would like to make the machines infer, okay, and then perceive. So for that inference is also needed. So essentially if we want to make any task automated, what we need is both of them. We would like to have the processing and then inference together. Okay, say for example, here is an example where there is in a fish industry, there is a conveyor belt, okay, on which the fishes are moving. Okay, and what the task here is, we would like to count the number of fishes and then we would like to classify these fishes into two different categories. Okay, assume that there are two categories, okay, salmon and sea bass. Okay, some fishes will be darker, some fishes will be brighter, some will be longer and some will be shorter, okay, and some will be tasty and some may not be tasty. So assume that these are two categories. So now we would like to put these into two categories. What do you think we should go about? How should we go about? Any inputs on this? Feature extraction, okay. So first do we see feature extraction, should we start immediately after this? Essentially what do we mean by feature extraction means? See, if I want to put these fishes into one of the basket, there are two baskets, one this side, one that side. Okay, based on the kind of fish I will put either this basket or that basket. But how do I decide to which basket should I put? Okay, I will find out some attributes of the fish image I have, right? I don't have fish, okay, we have only image of the fish. Okay, we would like to find out some features of it. Features means attributes of it. Attributes means what? Can you give an example for an attribute for this fish? Color, size, okay, very good, length, width and all those things. But the question is, if it is scenario is like this, one fish will come like this and one fish will come on the top of it and so on. Do you think I will straight away go for extracting its length, width and so on? What should we do? We do some kind of pre-processing. Usually pre-processing involves, okay, separating one fish from other fishes, okay, or one object from other objects, okay, and then aligning it and then making the measurements like the whatever intensity, average intensity, length, width and so on. Okay, so essentially any automated task usually requires some kind of pre-processing and then feature extraction. Feature extraction means finding attributes, and then the other third thing is I want to put these, given these attributes for me, for each sample I have, I want to put into one of the category. How do I put? I should decide all these category samples will have this kind of attributes. All these category samples will have this kind of attributes. I have to have the idea a priori. Based on that I can put, is it not? So that is referred to as classification, okay. So there are different ways of, for different tasks, different kind of either classification or few other things need to be done. But here we want to put into two categories, so essentially we need to do classification, okay. So these, if for any rough, most of the automated task requires these aspects, especially when we take the signals, either speech signals or the image signals. Now the question is, see, so far processing we have discussed. All pre-processing can be roughly assumed that we can do through processing. Feature extraction, okay, can we do processing? To some extent, yes. Okay, once I separate the objects, I can find out the length, width and so on. Classification, can I do through processing? That is also yes, in some tasks, but not in all tasks. Further, we see that the current methods in fact does through learning, pre-processing, feature extraction and classification as well. The elegance of the learning methods now are such that if we provide enough examples, they will they can be modeled and trained in such a way that we can perform reasonable pre-processing, feature extraction and classification or whatever the tasks as well. Of course, this is true in many other domains, and the kind of modeling etc. may differ from domain to domain. So if we consider that there is we will see now with a small example why the learning is required. Before that, just to see on what kind of features are more important. See, if I want to classify this fish into one of the category, we said intensity features. So if I take intensity, say the problem here is slightly different. We would like to classify cars and bikes, okay, and then what kind of features do you think are more important? I take the intensity feature at 2 pixels, here 1 pixel, here 1 pixel, 1 pixel feature here, 1 pixel intensity here, and then plot each sample. Say for example, if a sample has an intensity of 20 here and then 200 here, the sample will be 20 and 200. This sample is this. Okay, each point here is a sample. Sample means I have 20 cars or 20 bikes, there will be 20 points, okay, in this plot. Each point is measured by, each point is how do I place the point based on the intensity of pixel 1 and pixel 2, that is all. Okay, pixel 1 intensity I measure, pixel 2 intensity I measure, based on that I am just putting the points here. Okay, these are the samples I say. Now the question is, given these samples, can I separate the samples of say bikes to cars? Or do you think it is possible just if I measure the pixel intensities? It is not possible. What kind of features do you suggest better? As is seen here, handlebars, okay, and then probably handlebar may be good enough if we are able to capture, and wheels, okay. So these kind of features will easily enable us to separate these samples better. So if you want to perform any automated task, few things that are to be taken care is how to essentially processing, we have seen pre-processing. Second thing is on the feature extraction, what kind of features should we look for? So it also plays a very critical role, because the way we see the as we mentioned, the computer sees only numbers there, okay, and from that what kind of features do we extract? The way we see, the computer sees the object makes the difference, okay, and here in this example these are the features that are more important. So this assume that this is fine, but now we want to do it at a large scale, okay, we have a large number of samples with us. So we have assumed that say some 1000 samples, 1000 here fish samples, and we want to put them into 2 categories, okay. Initially we have taken, so what is this plot shows is, say we have measured the length of the fish, okay, the number of fishes having length of say 3 whatever centimeters, okay, is 7, okay, 7 fishes have a length of 3 centimeters. See, there are 2 colors here. One color shows the frequency of the fishes per different lengths for class 1, okay. The second plot shows the frequency of the fishes per a particular length for class 2, okay. So this is essentially referred to as class frequency plots. That means, so why do we need this kind of plots? Directly we can take the length, say if I want to classify or put these fishes into 2 categories, I can simply put the fishes having length greater than something to one class, less than something to other class, right. So why do you think we need to see the whole lot of fishes and then take the lengths of all those things, okay, and then only come up with some method. Why is that needed? Any guess on that? Say I am getting say 1000 samples of fishes, each length I have measured, they range from essentially 3 centimeters to 28 centimeters, okay. Then if I want to put into two categories, I know that sea bass fish is longer than salmon fish, okay, I can straight away put them by deciding something, right. So why do I need to see all fishes to decide and then put into two categories? Any guess on that? Is the question clear? There are actually two categories of fishes. I measured their lengths. The lengths are keep coming like 5, 8, 20, okay, and then 15, and then 25 and so on. We want to put into two categories. Okay, then what is the deciding factor to put into two categories? Threshold. Okay, now the question is, what threshold should I put? How do I decide? Based on I have a number of samples 1000. What optimization should we do here? Of course, we need to do what optimization we need to do. To look that, we need to see lengths of all samples. That's what we are doing here. Essentially, because see, for example, threshold I can put as 10, we can also put as 15, okay, but which threshold should we put? If I have enough training samples, I will see the lengths of all of them, okay, and then decide, okay. Usually what happens, if I see this, above this threshold I can put to sea bass class, and below this threshold I can put to salmon class, okay. So for that, usually it is the methods, most of the methods doesn't do with a single sample or two samples, we need to see a whole lot of samples, and this itself requires learning, okay. That means, because if I have enough samples, I will learn to know what threshold should I put, okay. So from this kind of methods, where we see the class frequencies or the number of samples per different lengths and so on, this essentially gives the distribution of samples, okay, across different lengths for class 1 and class 2. By looking at them, then we will try to decide. So we try to model the samples in terms of the probable density functions or of that class, or conditional density functions of that class, and then try to do something. Essentially, we will be doing some statistical modeling. We need to do some statistical modeling and use that information to learn the threshold, okay. From this this is something slightly different than processing, because we are not just using a sample by sample, and we have a priori knowledge of all samples, using that knowledge to bring in the threshold, to model the how the usual lengths are for different samples and so on, okay. So if you want to perform at a generic solution, you need to bring in some kind of learning. This is one aspect where the learning is important. If you want to do case by case solution, by some processing is okay, but if you would like to bring in a generic solution, some learning is required. So this is another example where, see, for this, if I put this threshold, still you can see that there are many misclassified samples. Then what can we do to reduce the misclassified samples? We can pick instead of length some other feature, maybe lightness here, okay. So even here there are some misclassified samples. Then what can we do better by taking to reduce further the misclassified samples? We may take them together, length and lightness, or width and lightness, two features together. So there comes the requirement of not just taking one or two attributes, or taking many attributes that describe a object or describe a signal or a sample of interest, okay. So that means if you want to describe through a feature vector or feature, it's not enough to take one or two features, so you need to take the essential features. All essential features are reasonable features or attributes to describe it, okay. And then if you would like to come up with a solution for the whole lot of samples or class of samples, we cannot get away with simple processing. There is some learning also needed, okay. So I will move on to the discussion for another example why the processing to learning is needed, and then discuss some of the aspects, different learning techniques. See, I will skip this slide, but this slide is self-explanatory. So essentially what it indicates is, say we initially started with signal processing, image processing, okay, where processing is important. Then we went to inference, that is computer vision does the inference, and the machine learning, pattern recognition, there the learning comes into the picture, and artificial intelligence encompasses the methods of machine learning as well as the rule-based methods. Okay. So essentially, let's get one more example why the processing is not enough. So assume that we want to do say face detection. Okay, we have a image. Okay, and then we want to detect where the face is. Okay, so if we want to do that, so there may be several faces here. So what do you think we should do? As we discussed before, so if you want to detect the face in an image, what is that we need to do? Find a filter that looks like a face. Okay, somehow I found a filter, okay, which is bright here, and then here bright means 1, dark means 0. Okay, and also I have used another filter. Okay, bright means 1 and dark means 0. So if I perform convolution with this filter, I may get some regions highlighted. Okay. See, but who will tell me to use these filters? See, in this example, by looking at the face, we are able to somehow bring and make or design these filters. But who will tell me to use this particular filter to perform to detect the faces? Okay, so there also some kind of learning is required. Okay, so to come up with the what features to extract or to enable the better feature extraction, learning is required. See, one more aspect is, say assume that we want to perform digit classification. Okay, we are writing the digits 5, okay, 1, 3 and so on. There are some probably 60,000 samples of digits. Okay, and then these samples are all handwritten digits. So 0 to 9, okay, 10 classes we consider, and there is a test sample. So these are all training samples. Okay, and then there is a test sample. The test sample may be, say for example, we have some 1000 test samples. Okay, and then these 1000 test samples are again some handwritten digits. So now the question is, if I want to classify this test sample to one of the category. One of the category means what are the categories we have? 0 to 9. So 10 categories we have. Okay, so we have actually 0 and then 10. So 0 to 9. So 10 categories we have. We want to put the training sample span over these categories. This is class 1 we consider, this is class 10. Okay, so we want to put this test sample into one of the category. Now tell me, what is the simple method that you know? What do you think is a simple approach that we can apply? Any method that you think. So this 3 I have image of 3. 3 means image of 3 I have. Okay, so let this be say 20 cross 20 image. Okay, and then these are also all images 20 cross 20. Okay, I have images of 3, 2, all those things. Okay, and we want to put this into one of the category. What category, how do I decide the category to which it belongs to? Any guess on that? We do correlation. That means compare this image versus this image. See if it is closer. Okay, because 5 and 3 are not closer, it may not be high correlation. I3 compare and 1 and 3, it may also be not higher. So whenever I have 3, it may have actually high correlation. Okay, so if I want to do that, how many operations should I do? E3 I have to compare with how many samples now? 60,000 samples. Okay, of course I see that each class, assume that 10,000 samples, not 10,000. So assume that if we put 6,000 samples, correct. So each class has 6,000 samples. Okay, so I will be comparing with all, say even if I take, I will compare with all 3s, okay, all samples. If I see that class 3 has class 3 has high correlation, okay, I may say that roughly most of them in class 3 has high correlation, then I can say that this belongs to 3, right? So I am performing 60,000 comparisons for deciding this test sample. Now I will move on to the next test sample. This I want to decide to which class it belongs. How many operations should I do? Again 60, same number. Next test sample. So for all 1000 samples, how many operations should I do? 1000 into 60,000, those many operations if I do. But if I have some model which reasonably learns and says that, okay, you just pass on through me, okay, the value for third class will be high, okay, if you just pass on to the model. No need to essentially compare with all 60,000 samples. You learn some model with all these 60,000 training samples. After learning, you have a small or some compact model, some model. Okay, you just pass on the test sample to that, and then simply this model already has learnt, okay, differentiating 0, 1, 2 and so on. Now, if I pass on the test sample to this, then how many the number of operations that I need to do in testing will be quite minimal, is it not? See, instead of 10,000 now, if I want to test 20,000 or 60,000 samples again, okay, those many operations I need to do again. Okay, so but if I have a model already learnt to distinguish them, it is quite easy to pass through the model and see. That's where the learning plays a critical or crucial role. Okay, so in all the applications, not just in classification and detection. Also, say for example, if you have a student grades, okay, you have some marks, we want to put grades on the marks. Okay, so what do you suggest? How should we put? So above 90, some S grade, okay, and then above 80, A grade, like that. Do you suggest me to put, or any other suggestion? We may see the, say for example, many of the students in the class has got, okay, so say 85 above, assume that, and then some other students has got so only in the range 60 to 70, okay, and few other students has got in the range, okay, 50 to and then probably 40 to 50, okay, then these are the major students in the class, okay. So should I put by to all the, so A for all of these students, and then probably B and then D? What do you suggest? So there can be some grouping, okay, on the marks. Based on that I may be able to decide grades rather than strictly thresholding. So that grouping is essentially called as clustering, okay. So usually if there are, say if I want to put all Indian faces separately, okay, together at some place in the features, okay, and then all foreign places faces separately. So should I decide case by case, or should I put thresholds based on intensities? So there should be some method of nicely grouping based on the features of the samples I have. Okay, this is referred to as clustering. So and then even for that we need learning, and there are, even if you are, there are other tasks, not just the supervised and unsupervised classification tasks. This is done usually by supervised classification. Supervised classification means where we have the training samples or some of the samples already labeled or known to be a particular class or particular object and so on. Unsupervised means we don't know, we just want to group them, okay, that is unsupervised. And some cases, what, say if you want to navigate a robo in an unknown terrain, okay, then what should I do? I can't learn and completely, I can't learn here and send it. Okay, we have to learn on the fly, or it should know how to navigate, okay, in an unknown scenario, or it should learn in unknown scenario itself. Okay, how does it learn? It's not by human guidance completely. How should we do? Is through some reinforcement learning, where we give the reward if it goes in a appropriate direction or appropriate way. We give a kind of punishment, or we take away the reward. Okay, if it goes in unpredictable or it's an adverse manner. Okay, so instead of giving the labels, we may encourage or discourage, okay, a learning through learning. So this is done in reinforcement learning. And even if you want to pick and place, many of the other scenarios also requires processing, but learning also, even compared to the processing, the learning also may be needed in effectively performing them, okay, because all the new scenarios may not always be enough for processing, so it has to have the ability to learn as well. So there are some methods that recent methods that does very well even in gaming, okay, through learning. So they in fact defeat the humans. So I will move on to the discussion on different category of the learning methods. Probably quickly in another 15 minutes we could wind it up. Okay. So there are different kinds of data. There may be some images, audio and text. For different kinds of data, we have different ways of extracting the information, and usually the pre-processing and feature extraction are application dependent, and the classification is not dependent on the application. So the classification is the where we have effectively need learning. So you can see that in different domains different kind of processing is required, different feature extraction is required. Here are few applications where the learning can effectively be is applied. So for example, here digit classification as we discussed, face recognition. For most of them to learn, you need good samples already to help us the learning techniques or to learn the learning techniques. So here it is, these are all the applications where you use biometric and face recognition, human versus non-human classification, biometric iris classification. These are few examples, and then identifying the different regions in an image. So as I mentioned, the broad category of learning methods are supervised learning, unsupervised learning, and then reinforcement learning and distributed learning. So there are different other categories that are also added, but these are the major categories. Supervised, as I mentioned, we learn from examples. Unsupervised means, so we try to group them. We are not bothered too much about getting the labels or getting guided by the examples. Okay, we just want to, we have the samples or their features or some attributes of the samples, and we would like to put them into different categories. Reinforcement learning, as I mentioned, it's not either by samples, it is by the scenario, and we have actually we provide either reward or the punishment based on the move it takes or based on the output it gives. And distributed learning takes not just a single agent for learning, you may have several agents and learning together, either in a collaborative way or in a competitive way. So there are some essential aspects when we want to understand or develop any learning methods. There are some few essential aspects. One is understanding what kind of data do we deal with while developing the learning methods. The data can be in terms of the samples and images, signals and so on, or can also be in terms of the different values at different nodes and so on. So that's one of the primary thing. The task we would like to perform, do we want to do it in a supervised way, unsupervised way and so on. And to learn, we should have a model in the sense that how exactly we make this learning happen, in sense that, say for example, there is an input and there is an output we would like to get. There is some relationship between the input and output. How do we model this relationship is the job of the model, and then to learn that model we need some objective function. Okay, that means we should say for all the class, all threes we should get the higher score when we have the test sample as 3 or when we have the input as 3. So that is essentially the objective function. And then the learning algorithm, there is some way that if we define an objective, how do we learn this model, and then essentially there will be some evaluation for the model that we learn. So these are a couple small examples for this. So here we are different CT scans, and we have actually the description of the CT scan in terms of the feature vector, and these are the labels. Say this can be a good scan or a healthy scan, and this may be a malignant scan. Okay, so we may have actually 0 for one class of the samples and 1 for the other class of the samples. Similarly, you have actually for all samples, and this is what the data essentially is. and this is an example of scenario of the data. And the task we would like to perform depends upon the application. Sometimes we may want to detect a face or detect a object, or sometimes we may want to perform some different tasks. So based on the task, we may define on what kind of scenario, like do we put it in supervised way, or through we put it learning a class label only, or do we put it getting a output value, etc. So the model, the example for model is essentially finding out the function that relates the input variables or input features to the output variable. Okay, output variable can be a class sample, or can be a value that we would like to see for a particular, say if you want to find the cost of a region, what I will see, I will make some attributes of it, say how much is the region, I would like to find out the cost for, and where it is located, okay, such things. Those are all the input features, x are input attributes, and then the output may be the cost value. So, so that's how the model will try to give a relationship between them. And then given the input output relationship, we want to see a loss function, that is we would like to see that I know already that in this region this has to be high value, okay, in this region cost has to be low value. So I will try to match with the ground truth or the knowledge that inference we have, and then or the that is supposed to be performing, and then we try to perform a formulate a loss function or a cost function or an objective function. And then the algorithm role is what? Try to find out a best f or best the model that will relate the input variables to the output variables agreeing with the ground truth. Essentially there are different optimization procedures to or different procedures as such to find out the model, and finally we evaluate the model that we develop. So supervised methods, there are different kind of supervised methods. You will be seeing some of them in this workshop. So one class of methods try to discriminate the samples of one class from other. That means they are only interested in putting a separating line between the samples of one class to other. That means faces versus non-faces and so on. Some other methods try to model them by like the probability distribution as we mentioned at the beginning, and use those probability distributions to put the thresholds or demarcations. So by the nature of the methods that are developed, these supervised methods differ either as discriminative or generative. Similarly, there are different clustering methods, grouping methods. For example, this is referred to as k-means clustering, where we would like to group the samples based on deciding a priori how many groups we have in that samples. So we may a priori decide that there are 3 groups, we group into 3 groups, okay, and then how do we group? Based on some distance measures and bringing the samples close to that, okay, the mean value of that cluster. That means we initially decide 3 seed values or 3 centroids, okay, and then we would like to see that the samples all close to that centroid or mean values will become one cluster. Like that we keep updating, assigning the samples to that mean and updating the mean from the samples of new samples that we get in. Similarly, there are other kind of clustering where we do not a priori decide on the number of classes, but we start with grouping the closest samples together and finally try to see where we get the best clusters. Should it be 2 clusters, 3 clusters, 5 clusters, we decide later. This is referred to as hierarchical clustering. So these are also based on distance matrix. So there are different variety of reinforcement learning techniques. So you will be introduced to some of them. So there can be policy based, value based or model based techniques, where the aim is not to find out a mapping between input and output, but we would like to give if say if there is a correct move from the agent, action from the agent, the environment assesses it and gives a reward, and if there is a wrong move, the environment gives a punishment or a negative reward. So it's learnt in that way. So there are you will also be listening to distributed learning methods and applications, where there are some cooperative learning and so on. With these learning methods, we have plenty of learning systems that are in place. Few of them are very successful. As you can see, smart cameras where we can detect the faces and so on, and then self-driving cars in some constrained scenarios we have them, and distributed sensor networks and so on. And learning can be online as well. That means once we deploy the method, during the operation of the system, also it can learn. That is referred to as online learning. There are some very celebrated breakthroughs in this area. So starting from that too, in the recent years, there are several breakthroughs which were not, in fact, not at all possible before. So we will see the methods that has given rise to them, and there are some examples are here. So fighting with the spam mails and then playing the games automatically, image classification detection and generating the images now. So we can generate through programs the images of different objects, faces and so on, and robotic navigation and so on. So anyway, we will discuss them later in the subsequent talks. So we see that some of the developments currently even surpasses the human accuracy in terms of the annotators annotating very 1.5 million images. When the human annotators annotate 1,000 classes of images, the accuracy is 5%, the error is 5%, accuracy is 95%. Now the models, even in 2015, they cross the percentage of accuracy that with which we can do the classification on large scale. However, there are some other tasks or many tasks where there are still challenges that cannot even reach the human accuracies. This is another celebrated example where language translation, so which was not very simple before, now reaches to the human accuracy. So there are different other examples. This one caption generation, like if we see the image and give an inference, camera also or the computer program also can see and give an inference. Writing, so it synthesizes the writing itself, and you can see the links. So it if you just utter a sound video by hitting an object, it's a just if you hit it, if you provide a video to the algorithm, it itself utter the sound. So it can mimic, it is lent in such a way that so you can see the the computer mimics the sound. So they are only providing a video to the algorithm, and algorithm is producing the sound. So you can anyway see the video from the slide. So this is all possible through learning methods now. So here are some examples, instances that are done in the lab, making the snapshot of the panoramic view of the lab and then detecting the faces and giving the attendance or giving the recognition of the faces. Some of the students have developed bringing attendance from these classrooms where they have automated the process of registering each student's face and then giving the attendance. And there are not just in some of the fields, in many of the fields this learning has shown great progress in terms of in medical field. One example is to classify the cells in imaging flow cytometry, where we do not add this time directly. When the small sample of blood flows through a fluid, we can count the number of cells and we can classify the cells. And these are some examples in the satellite image processing where we can identify roads, buildings in different kind of images and identify these landslides, region of landslides and so on. Here are some examples of clustering where you can where the clustering of clouds happens. So you can see this video where the clustering of cloud happens, and here are some other examples where tracking of different objects is happening. So you can see that there are plenty of examples where these learning techniques play a good role in terms of reaching to the or approximating to the human accuracies, or tending towards human accuracies. The workshop is essentially you will get to know some wide variety of techniques that will enable you to understand and apply. So here are the references, and thank you.